speaker is Jan Urbański, who is a lead developer at New Relic, an application performance monitoring company. He's a very active open source contributor. The projects he works on include Postgres embedded Python bindings, Postgres driver for Twisted, and Twisted connector for Pika. He's a regular speaker at Postgres conferences and PyWaw meetups. Jan will talk about combining Python and Postgres. On snakes and elephants, Jan Urbański.
Good morning. I'm Jan, and I approve this message. That was a very good question. Thank you for the last question. I will be talking about running Python code inside your Postgres database. Is this a Python conference or a Postgres conference? I might have walked into the wrong room, but that's fine. You'll sit through it. The slides will be there. You can get the PDF. And this is more or less the outline of the talk. We will talk about stored procedures in general, just as a refresher, what are stored procedures, how to use them, about how Postgres implements stored procedures, then about PL Python, which is, spoiler, an implementation of stored procedures in Python with some examples, and then some real-life applications on how you would actually use that feature instead of just rendering Jinja templates in your database. That's cool. There's more cool things that you can do. So stored procedures. Stored procedures in databases is basically procedural code that you can call from SQL. So it's something that's accessible from the SQL. I'm going to say SQL or SQL. I'm going to change those two because I'm the native speaker. So it's procedural code you can call from SQL. Now, why would you want such a thing? It's typically used for implementing operations that you can't express easily in SQL. So things that really need to go, I don't know, row by row, or affect some external system, or do some operations that SQL just is not good at. And they're also used to encapsulate bits of business logic. So you don't have a huge query or a series of queries. You just have an encapsulated procedure that captures the logic of those queries. So here are some examples of how would you call procedures, and this makes it obvious what would you use them for. So let's say I have a procedure that says purge user records. This, I guess, would be the user ID, and then I would just call it, and the user records would disappear. And I don't really have to know underneath, is it deleting from 3 tables, 7 tables, what's it doing? It's just encapsulated logic. The lower function is actually, you could call it a stored procedure. It's a piece of functionality that in SQL would be, well, it's not really on the level of SQL because it's operating on a single datum, so it's exposed as a stored procedure. And triggers, that most of you know how they work, triggers are typically stored procedures, because a trigger is a procedure that runs when something happens. It's not really SQL, purely SQL. And so most relational database management systems have a blessed language that you use to write your procedures. If you're unfortunate enough to work with Oracle, you will be writing PL SQL. Or you will be writing Java, which is so sad, I haven't even put it on the slide. If you're running MS Server, you will be writing Transact SQL. Now, as a common theme to this talk, Postgres is better. This will reappear several times. So how do stored procedures look like in Postgres? What are stored procedures as far as Postgres is concerned? In Postgres, a stored procedure is 3 bits of things. It's info about input and output, so it knows, it's a thing that knows I'm accepting an integer and a string, and I'm producing a string. It has some additional metadata, because you have a name, so you can call the procedure, you can name it, and essentially a bunch of text, just a blob of text. That's a procedure. Now, a procedural language is just an extension module, one you can write yourself. You have to write it in C, unfortunately, but it's not, rocket science. It's just a bit of code that exposes a single function. It can expose more for additional functionality. It has to expose one single function that takes this bit of text and executes it. And that's it. That's as simple as that. Just execute some code, some string, some text. So how does this really work internally in Postgres? And then we'll see how this builds up into allowing Python to be executed inside the database. Like I said, Postgres is better. You can write stored procedures in any language, as long as there's a handler, right? So you can't just dream up a language. But if there's a handler, you can write a procedure in it. And some languages are supported officially. When you install the core distribution, you get those. And these include PLPGSQL, which some of you, if you work with Postgres, might have used. It's something designed to ease porting from Oracle's PL/SQL. So some of the design choices for PLPGSQL are driven by what Oracle did. So they're not very, sometimes it's painful to work with PGP-SQL. There are others, like PL-Tcl. There's a typo there, it's Tcl. There's actually Tcl supported inside your Postgres. I've never seen anyone write PL-Tcl code, but it's OK. There's Perl, and there's Python. So these three are out of the box, supported by the core development team. And there's a lot of others that you can download and install. There's one for Ruby, which is not that interesting. If you have Perl and Python, why would you use Ruby? I mean, it's fine, but it's in the end, it's the same thing. It's just a scripting language. There's Lua, which gets interesting, because Lua can get pretty fast. You can use it if you want your stored procedure to run really fast, but you don't want to write C. There's PHP, whatever. There's Java, if you really feel like it. There's Scheme, which is awesome. There's V8, which is getting very popular now, which means you can write your stored procedures in JavaScript. Some people like that. It's not my place to question them. There's R, which means you can do your mathematics analytics in R inside the database. And there's a bunch more. There's Erlang, I think. There's a whole bunch of crazy stuff. So the point is, since the design is a language handler just takes a bit of text and executes it, that text can happen to be a Python script. And then as the Python language, the C implementation has the ability to pass it a bunch of text and have it executed, this is what you use to build up PL Python. This is how PL Python is built out. There's a distinction in Postgres between trusted and untrusted languages. Trusted languages are the ones, well, if a language is trusted, any user can write a procedure in this language. So like PLPGSQL, you can just log into Postgres and write a PLPGSQL procedure and call it. Those languages need to provide a sandbox environment because they will be running arbitrary user code, right? So you will, if you allow a user to write a PGP-SQL function, you basically allow the user to execute arbitrary PGP-SQL code. And that's usually fine. So PLV8 is a trusted language because you can sandbox a V8 JavaScript implementation and lock it down so it's safe to allow users to execute arbitrary code. And all the languages that are not trusted are untrusted. And untrusted languages can only be used by super users. So you need to be a database super user to define a procedure in an untrusted language. Now, the question is PL Python trusted or untrusted? How do you feel? Yeah, PL Python is untrusted. And here's the thing. It used to be trusted. So there used to be a version of PL Python that was trusted. Just like there's a version of PL Perl that's trusted, because the core developers believe that you can lock down an embedded Perl interpreter to make it safe to run arbitrary user code. They used to believe it's possible for Python. And then after a bunch of exploits, a bunch of bug fixes, they just said, no, let's drop it. Python is an untrusted language. And here's the thing. If someone would come up, it's one of the fields where Python is lacking, actually. The ability to embed a locked down version of the interpreter to allow users to execute arbitrary code, but within a sandbox. Something that V8 has built in, something that Perl has solved, Python has not solved. You can escape from any sandbox that people have devised, which makes it an untrusted language. And why is this important to us? Because this means you will not find PL Python in Amazon RDS, right? Amazon can't allow you to run arbitrary Python on their database instances. You won't find it on Heroku Postgres. Same reason. You will not find Perl on Amazon or on Heroku, even though they're trusted. I think they're not trusted enough by Amazon and by Salesforce. But PL Python is explicitly not trusted. So PL Python, the actual implementation, the actual guts. In so many words, it is the ability to run Python inside your database process. I'm saying backend, and I might be using that term. In Postgres parlance, a backend is the process that you're connected to with your client. So like if you run your Django app, the Django app connects to Postgres, and Postgres starts a new process called the backend, and this backend is what you're talking to. So this is a Postgres server process that services a connection, a backend. It runs inside that process as that process's OS user, so it can do anything the database can do. It can access all the database files. It can read all the data from the database. It's bypassing the normal authentication mechanisms built into SQL, into everything. You can just read the raw files. So it needs to be untrusted. And it can run arbitrary Python code. And here you can go crazy. You can render Jinja templates, but you can go much further. And sometimes, it's fun. And sometimes it might even be useful to go further. We'll see. Because that's the fun of it, just being able to do those things. So how does this work on an even lower level? The backend process starts an embedded Python interpreter. So CPython has an embedding API, which some of you might know. It allows you to just start up an interpreter, and then you use it as though it was a Python shell. I'd say when you type Python at your prompt, this process starts an embedded Python interpreter. So this is more or less what happens in the server process. There's a Python thing starting, and this is slow, because Python startup, it's a 5 megabyte library. It needs to initialize all those memories, caches, look up dictionaries, create all those initial objects, the built-ins module. It's slow. So you do two things to make it palatable. You preload the shared library so that when you pay it on server startup or on connection startup, not when you first call the function. So you can preload that. And you can use long-lived connections. And you're reasonable people, you use long-lived connections, right? You use a connection pooler, and you keep Postgres backend spun up for long times. You don't open and close connections all the time and make Postgres create a process for you and shut it down all the time. You do use a pooler, so that's fine. And then there's, it works by, like I said, a procedure defines input and output types. So what Postgres will do for you, if you use PL Python, is it will translate Python types into Postgres and vice versa. So your Python procedure will receive Python types, even though you call it from the SQL level where you operate on Postgres types. So if you call a PL Python procedure passing an integer, it's a Postgres integer, right? But inside your Python, you will have it available as a Python integer. And same for strings, and the same for lists. So a Postgres array will appear in your code as a Python list. Returning a list will make Postgres interpret this as an array. So it does the type translation, but just for primitive things. So if you return some random class, PL Python will just call its string method and return this as text. And this is, it basically will say, I don't know how to cast this from your Python type to my Postgres type. And the same goes for input. If you call a PL Python procedure with passing it a value of a type that's not castable to Python, then inside Python, you will receive it as a string that you will have to parse out yourself. But for the basic things, it more or less works. And we'll see that it covers 90% of the use cases. How do you, so think about it. You have Python code, and you need to somehow inject things coming from the SQL level, from outside of the actual Python script, into the script. The decision PL Python took is that variables appear as global variables. So if you call a function with some variables on the SQL level, it will appear in your script, and it will be available as a global. We'll see an example in a moment. there's also a magical global variable that holds utility functions. So you don't have to import that module that holds those functions. It's available to you inside your execution environment. It's not a very, I mean, it's not a very opportunist decision, but it has to be kept that way now that there's all that legacy code written for PL Python. That magical thing is PLPy, a module that inside holds stuff specific to PL Python that wouldn't make sense in just a Python script. We'll see how we use that. And there's a couple of dictionaries that you get passed in that you can use that are persistent across connections, that basically give you shared memory. And in and of itself, it's interesting because this means that you can get easily just shared memory that you can put arbitrary stuff into and read them later on across your session, your SQL sessions. You can put stuff there, do some other queries, then call another function. That other function will see that first function's result in the cache. And we'll see an example of that. One thing to have in mind that if you want to configure Python path to have modules importable from, I don't know, your virtual and whatever, you need to change the processes server's Python path. You don't just run PSQL or Django with a changed Python path. The server needs to have the changed Python path because it's the server that's importing stuff. It's obvious if you think about it, but it's hard to wrap your head around it the first time you encounter it. So we actually have to modify the server's environment to get a Python path with your own modules. Two examples. I talked a bunch. Let's see how this thing actually works. It's Python, right? So just plain Python would not be that interesting. The interesting part is using things that come with Python, like NumPy. So let's say I define a function, call it histogram. I tell it, I mean, this is SQL. Up to here, it's Postgres syntax. It's fairly readable, and I think some of you might, I hope some of you at least are more or less familiar with how SQL works. So you basically say, there's a histogram function, I pass it an array of floats, and an integer called bins, whose default value is 10. And I return an array of ints. Up to here, we were speaking Postgres. Between those, we're speaking Python. So this is our text. This is what's going to be executed. And we just import NumPy. We get a histogram. And as you can see, A and bins just appeared in the program, because Postgres will inject those as globals to this script. So I tell it, give me a histogram of the array with the bins, and the histograms in NumPy return the actual number of things in each bucket and the boundaries, I think. So here I'm just taking the counts in each bin. And there you have it. I return an array, and Postgres will interpret this Python integer array as a Postgres integer array and make it available to me as on the SQL level. So this, it looks really readable and nice, but there's an appreciable amount of magic going on here. But it's good magic. It's magic that's hidden from us. And I can actually go and here's my Postgres prompt. And I can try and select, well, let me just show you first. I have a table here called common crawl URLs, which is a table that has, sorry, I do not. I'm going to try and, yeah, so it has two columns, the ID and the URL, and just a bunch of URLs. I just got some random URLs from common crawl, right? So what I will do is I will get the histogram, right? So here I'm calling the histogram function, and I'm passing it an array, and the array is built out of the lengths of the URLs. right? So if there's for each URL, I'm calculating its length. Then I'm building up an array of those numbers, and I'm drawing a histogram of those. Just to make it clearer, I'm going to get rid of those, and you'll be able to see what's going on more easy, right? So we're getting an array of the lengths and getting a histogram, and effectively, we have a histogram, right? This is NumPy that calculated stuff for us. This could have been whatever matrix transformations you want to do in NumPy. We just calculated this inside of Postgres. We know that the first bin has almost all the URLs. I think it's your normal power law thing. Most of the URLs are of the certain size, and then there are some stragglers, and then there's very few URLs that are overly long. So this is how we built up a Python array, and then we passed it to NumPy. And now let me try and get back to my presentation by alt-tabbing like I shouldn't. You can use other modules, and there's some other examples I have here. So let's say I want to parse out the hosts from those. I want to have a report that says how many URLs I have per host name, right? Parsing that out in Postgres would be annoying. I would have to parse the URLs. It would be rather fragile. Parse it with regular expressions, whatever. I can just parse them out in Python and have a function that gets past a URL and returns the host name. And just like that, I just had a function that I can use in aggregation. I can use as if it was a built-in function. You can use, let's skip over that one and go into utility functions. So here you can see the PLP module giving you access to utility functions that only make sense inside Postgres. Especially PLP Execute allows you to execute a query inside your stored procedure. So this means your procedure can go on and execute, get some other data it needs to continue operating. And it's nice because you already have the connection. You're running inside a Postgres process. So you can just go and execute arbitrary SQL and get data back and process it in a way. So this function should be pretty understandable. What we do is we have a function that's called add unique user that gets passed a name and an email. And let's say the email, the username needs to be unique. So what I do here is until I'm able to actually execute it, I try to create the user. So I try to insert into users those values. If I get a unique violation, here you can see I have a special exception provided by PL Python called unique violation. I append an underscore to the name, and then I try again. And once I'm able to actually insert the user, I'm returning the name that it kind of generated. So this will make sure the user got inserted and tell you what username it ended up having. So things like that would be annoying to do in app code or just plain ugly. Here you encapsulate it, and the application code just says add user, and the user appears. Here I have an example of using caches. So as I said, you have some global dictionaries. The global dictionary is called GD, global dictionary. And so and this is just normal Python things. What I'm doing here is for a domain that I'm passing to the function, I'm trying to get something from the cache. If I found it in the cache, I'm just returning it. And if not, I'm doing a DNS lookup, caching it, and returning. So here you can see, and I'm using an DNS lookup just as an example of an operation that takes time. But it can be anything. It can be any calculations that I've already done and I want to cache. And it's an easy way to get a poor man's cache inside your Postgres. This cache lives as long as your session lives. So when you disconnect and Postgres shuts down that backend, this cache will go away. But it's pretty much OK if you have a long-running connection. Over the course of n queries, it might be beneficial to just have this little simple cache. This is an example of a trigger. So I would define this saying returns trigger, and then this would make sure that if I insert a user, I will only be able to insert users that have a domain name with a valid MX record. And it's actually code that's been running in production for a system, actually for the PostgreSQL community forum. They would validate that the email you're registering with, the domain name, has a valid MX. I'm omitting error handling here, and of course this is just a sketch, but it's one of the things you couldn't do otherwise. You couldn't do just a network request from inside your backend. Here you can because it's just Python. And this is, well, it's an example of doing yet another crazy thing, like progressing in the craziness scale, where we actually pass in a URL, and it gets the vCalendar, an iCalendar source from that URL, and yields events on that iCalendar. So I could pass this function, schedule, an arbitrary iCalendar URL, and it will give me a table of those events. Let's see if I can actually, right, so I have here this big URL, which is the URL for Python events. And I'm saying I just want ones where locations like Poland. So let's see if I have internet connectivity here. And yeah, I'm probably not connected to the internet, but this would basically go off to the internet, fetch the iCalendar, and give you the events. And you can then filter them as if they were normal Postgres responses. So you can do a like, you can do where, you can insert stuff. And so, okay, you've seen that you can do things ranging from reasonably useful up to outright crazy. How would you use them in real life? Why does this actually, would you use them in real life, or is this just a gimmick? So here are some examples. What I did a lot is I had a piece of logic I needed to write, and I didn't want to write it in PLP SQL because it's ugly, because it's cumbersome, because it's a drag. So I just wrote it in Python. Just pure logic, just manipulation of some data, splitting out something, parsing out a host name. Those little bits, you can just write them in Python. You can do some NumPy stuff, and I've seen companies doing NumPy stuff, pretty heavy NumPy stuff, which means you don't have to ship out all the raw data to a computation node, compute, and then store back or report or whatever. You just compute right inside the database where the data is locally. You can do some language analysis. Python has those wonderful toolkits for language models. You can just use them where the data is without shipping out raw data outside of the server. You can check if a column contains a valid protobuf stream. So we can have a check constraint that tries if the column is valid protobuf objects. I know that some people are, for instance, storing protobuf objects, treating it as a cache or whatever. You can do all those things. You can do caching, like I told you. You can open connections to other instances and run queries there, right? You can just import CyclePG, connect to a different server, and run stuff there. Actually, Londist is a system that did replication through PL Python triggers, if I'm not mistaken. So because it's just Python code, you can just grab the row as it's written, connect to a different Postgres, write it there. Boom, replication system. And you can do HTTP requests, whatever. So let's skip over multi-corn and go back, because I think I'm running out of time, to some best practices if you end up doing this. And I encourage you to try, because it might be a valuable addition to your toolbox. First of all, versioning. Keep your PL Python code in a module inside your app. Version it with your app in the same version control. Just keep it as a module. And all your SQL functions, just make them two-liners, like that. You import the function, and you call it. And that's it. You never write anything else in Postgres. All the logic lives with your application code, and you pass the magical PLPy module, all the rest, through this. This means that you can also unit test those by just mocking out wherever the PLP magic thing and the variables are coming in. So it gives you a nice power on how to work with that. And remember, you are running inside the Postgres process. So if you crash, if you segfault, it's going to be disastrous. Just don't overdo it. It's easy to overdo it and render templates or do. I mean, rendering templates is not a very bad thing to do. It's why not in the end? You have to render them somewhere. If you have computational power in the database, great. But just be careful, don't overdo it. But do try, it's fun. Thank you.
Thank you for your talk, Jan. We've got a little bit of time for the Q&A session. So if there are any questions, please raise your hands.
So from your experience, what are your feelings about debugging that stuff? When something goes wrong, does it give you like a mixture of C plus Python plus SQL to process,
No,
or is it readable?
it won't give you C unless you segfault, and then you just send a bug report to Postgres bugs. It won't. It will give you reasonably readable tracebacks. I mean, I can try and call. The actual problem I saw here, see? The bug says, connection aborted, name on servers not known, DNS is down for me. It's a readable error, it's fine, you can live with that. So debugging is not that painful, especially if you keep the functions just two-liners, because then it's just all Python. And then you don't have to ever dive into SQL, just pure Python.
So I have the question about connecting with another database, another databases from inside of Python. So
you can do anything Python can do. So you could just open a connection to, you can import the Oracle module, connect to Oracle database, and clear a cache or run SQL. You can do whatever. That's the thing. What you have to think is, if I'm not overdoing it, if it's not too much. What I've used it for myself is cache invalidation, for instance. You have a database system and some cache that's read-only, that's there to avoid hitting the database on each request, right? If something changes in the database, you need to invalidate the cache. If you write a trigger to connect to your cache and make it invalid, let's say varnish. This means that any application, any developer that writes anything to the database via a trigger will invalidate the cache. They don't have to think about it. Any application that will, you have a Django admin that's used to create a field, to create a new entry. Django admin will not go and invalidate your varnished. But because the underlying storage changed, a trigger there goes and invalidates your varnish cache, right? So this means that you cannot have an invalid, a stale cache, because you've added the invalidation code to the very bottom where the actual truth is stored to the database. So there are valid reasons why you would want to do things like outbound network requests from inside your database. For connecting to other databases, you'd usually just use dblink, which is an extension that just does that. Or you would use foreign data wrappers, which is another mechanism in Postgres, to connect to external data sources and present them as if they were local. There are better solutions just for that. But varnish cache invalidation, I've seen that in production, and it worked pretty well.
And the last question.
Okay, so thank you for giving this talk. It was really inspiring, and I've got a pretty difficult questions. Maybe for me it seems to be difficult. Once you've put such a code in production, have you got any smart solution to monitor somehow behavior of this code, like being executed on Postgres, because you put like another brick into your system that may potentially fail? So are there any smart things to track somehow how it works?
So unit test that code before putting it there. So just make sure that Python code you put there is unit tested. Have some errors in your code in the database will show up just as errors from Postgres. You just get an error. So trace those errors, use something like, I want to say Sentry, use something like New Relic, right, that monitors errors for you. But just keep an eye on those, and it's not very different from debugging any other stored procedure, or for that matter, any other query. Just keep an eye on long-running queries, keep an eye on logs, transactions not being closed, the things you would monitor in a database anyway.
Thank you.
There are still some questions that people would like to ask, but we have run out of time. So please catch Jan in the meantime. And thank you, Jan, very much.